Lecture 11, Part 3. I would like to say about site investigation because this is very important. And site investigation. This is very important, and to establish the suitability of a location for the proposed work, a site investigation is normally undertaken. This typically involves 3 stages. Deck study. A geotechnical engineer will search through the relevant maps and documents in order to discover as much about the site and its surrounding as possible. For example, the following information will be studied: geological solid and draft maps, hydrogeological maps, ordnance survey maps, including historical versions, aerial photographs, past activities within the area such as mining and waste tips, public utilities, etc. The next stage, site reconnaissance. A geotechnical engineer visits the proposed site and undertakes a visual inspection. For example, tree cover will be assessed as this can indicate soil type and saturation levels. Also, willows trees require very wet ground. The next stage, ground investigation. The only true way to ascertain the underlying soil conditions of the site. During the investigation, accurate information relating to water should be obtained. Suitable soil samples for both visual classification and laboratory testing should be extracted. This could be in a disturbed or undisturbed state, the latter representing the exact in situ state of the soil, for example in terms of moisture content and degree of compaction. The soil samples are normally extracted from the ground by drilling some form of boreholes or excavating a trial pit. From the information gained from the site investigation, the following inter alia should be established: adequate and economic design to be prepared, the best method of construction, suitable use or disposal of in situ materials, the changes that may arise in the ground and environmental conditions as a result of work. Terminology used in soil surveys. Soil series. A basic unit of soil classification, consisting of soils that are essentially alike in all main profile characteristics. Soil phase. Subdivision of a soil series of other unit of classification having characteristics that affect the use and management of the soil, but which do not vary enough to merit a separate series. These include variation in slope, erosion, gravel content, and other properties. Soil complexes and soil associations. Naturally occurring grouping of two or more soil series with different use and management requirements, which occur in a regular pattern across the landscape but that cannot be separated at the scale of mapping that is used. Soil complexes are used to map two or more series that are commonly intermixed on similar landforms in detailed county soil maps. Soil associations are utilized in more general and less detailed regional soil maps. Map units are the actual units which are denoted on the soil map and are usually named for the dominant soil series and slope phase. Map units generally contain more than one soil series. Units are given the name of the dominant soil series if more than 85% of the area is correlated as a single soil series. Each map unit is given a symbol, numbers of letters on the soil map, which designate the name of the soil series or complex being mapped and slope of the soil. Soil strength. The strength of soil is defined in terms of its shear strength. You can see on this figure a shear strength of soil. This is shear surface and the relative displacement of soil's mass. This is the maximum shear stress that can be applied to the soil in any direction. When this maximum has been reached, the soil yield is regarded to have failed. There are two components of shear strength: friction and cohesion. Pore water has no strength The value of cohesion and friction are known as the shear strength parameters. In 1773, Coulomb developed an expression for these parameters, which defines a straight line failure envelope. Where C apparent cohesion, angle of shearing resistance, and sigma normal stress of failure plan. Here you can see a normal stress, a diagram of normal stress from shear stress from Coulomb general failure envelope. In certain soils, both cohesion and friction contribute to shear strength. However, in other soil types, only one of the shear strength parameters may be present. The failure envelopes in this figure and this figure illustrate a range of soil type. For example, failure envelope for frictional soil. Diagram of shear stress from normal stress, and this is indicates that undrained saturated clays and silts only cohesion have friction 0 and for undrained strength envelope. And failure envelope for cohesionless soil, here sand and gravels, only friction, have diagram from of shear stress from normal stress with angle of shearing resistance. Settlement and consolidation of soil. When a soil is subjected to an applied load, such as form a newly constructed building, a degree of compression will probably happen. And there are four main types of settlement that can occur. Immediate settlement occurs instantly upon loading and is a recoverable elastic deformation. That is, it will expand to its original volume if the load is removed. This type of settlement is usually small and occurs during construction. Second, consolidation or primary settlement results in a decrease in the volume of voids. This type of settlement is not normally recoverable on the removal of the load. In a saturated soil, the decrease in voids also results in the dissipation of excess pore water. The rate at which this type of settlement occurs depends on the permeability of the soil. High permeability soils, such as sands and gravels settle quickly, thus increase in effective stress occurs over a short time period. Low permeability soils, for example silts and clays, require a longer time to settle or consolidate, years, thus the increase in effective stress is slow. Plastic deformation or secondary consolidation is due to lateral flow of soil particles and is recoverable on the removal of the load. And the last type of settlement. Creep occurs in organic soil. For example, peat, due to the collapse of fibrous matter and it's not recoverable on the removal of the load. Of these four types of compression, the greatest contribution to the settlement of a structure is generally consolidation or primary settlement. Thank you for your attention. And now, quick quiz. What are the four main groups of soil? What are the two types of engineering soil? What influence does moisture have on a soil? What are the two types of soil density? What are the two components of shear strength? Why should a site investigation be undertaken? Vocabulary: soil, granular soil, cohesive soil, bedrock, mineral material, silt, gravel, weathering, aggregation, vegetation, fertile, porosity, density, drainage, composite, composite materials, fibers, sheets, particles, matrix, fiberglass, glass reinforced plastic, Kevlar, Young's modulus, timber, hardwood, softwood, cell, seasoning, plywood, shipboard, kiln, distortion, decay, rot, fungi, deterioration, polymer, monomer, plastic, thermosetting plastic, thermoplastic epoxy, polyesters, polyurethane, polyvinyl chloride, polyethylene, composites, fiber-reinforced plastic, concrete, cement, component, aggregate, hydration, kiln, gravel, furnace slag, expanded clay, fly ash, pumping, clinker, mixing, placing. Bolt furnace, tank furnace, annealing, shaping, melting, amorphous, silicate, silicone, sodium, potassium, calcium, lead, zinc. Lime, oxygen, acid, flint, alloy, blast furnace, ore, corrosion, malleable, ductile, electrolysis, carbon, aluminium, brass, iron, copper, steel, bonding, alloy, shear force, atom, neutron, proton, electron, stiffness, elasticity, melting, fracture, creep, fatigue, crack. Building materials, environment, concrete, metal, steel, timber, insulation material, polymers, clay, glass, gypsum, bitumen, transparent, bendy, rigid, soft, hard, liquefied.